We demonstrate Panda, a weakly supervised system for entity matching. Panda adopts the labeling function abstraction and features an IDE that allows users to easily write, debug, and combine labeling functions to generate a large amount of labeled data quickly. The IDE has 4 panels: the EM stats panel that monitors the core statistics of the EM task, the labeling function stats panel that monitors the core statistics of the labeling functions, the data viewer panel where the tuple pairs will be shown, and the labeling function authoring panel where we are going to write labeling functions. Let's use Panda for a concrete example. We use the well-known real-world dataset ABTBY. We upload the dataset by providing a path to it and click on the button Load Data. A progress bar appears showing what the system is doing. The system has loaded the tables, performed blocking, and now it is discovering labeling functions. The table info and blocking info are shown in this panel, and the discovered labeling functions are going to be shown in this panel. The system also automatically created a Jupyter notebook with all of the discovered labeling functions listed, and all of the required libraries imported. In these 2 panels, every value colored in blue is clickable. We can click on the name of a labeling function to say its code. We can also click on matches to say the matches found by this labeling function. Every big row contains a tuple pair. Blue indicates tuples from the left table, and purple indicates tuples from the right table. We can see most of the tuples are actually matches, which means the quality of our discovered labeling functions is high. Let's say we are not satisfied with the discovered labeling functions and want to find more matches by manually writing labeling functions. To do this, we need to look at some informative tuple pairs to come up with some ideas. We can specify the number of tuple pairs we want to see and click on the Show button. The system runs our smart sample method and shows some likely matching pairs that are abstained or labeled as non-match by the current labeling model. To get a better view of the data, we can drag to expand the data viewer. A matching likelihood column is provided, and we can use it to sort to quickly identify matches. For example, this one and this one are both matches. We can see the name attribute of the matches has many common words. Based on this observation, we come up with an idea that a tuple pair should be a match if there are many common words in the name attribute. We now go to the notebook to implement this idea by writing a labeling function name overlap. We can use many existing utility functions imported here, and we can also refer to the automatically discovered labeling functions. To write our labeling function, first we need to convert the name attribute to words. To do this, we can directly copy the pre-processing function from AutoLF0. This converts the name attribute to lowercase and split by space. To compute an overlap score, we can also copy the weighting function and Jacquard distance function from AutoLF1. Finally, we obtain an overlap score, and we want to return a decision based on a threshold. If the score is low, we return non-match. If the score is high, we return match. Else, we abstain. We apply the labeling function by running the cells. We say the stats in these 2 panels are updated. If there are errors applying the labeling function, we can turn on the debug mode. This allows us to debug code as in a coding IDE. For example, we can set breakpoints. After a few iterations, we have written many labeling functions based on many heuristics, such as product price and product size. Now we want to improve the quality of existing labeling functions by quality debugging. We can directly click on estimated false positive rate to sort. We can see the labeling function name overlap has the highest false positive rate. To debug, we can click on the number. The system shows the tuple pairs that this labeling function labels as match, but the combined label says no. We can see these false positive pairs do not have enough word overlap in the name attribute. Therefore, we go to the notebook and increase the threshold of being a match from 0.4 to 0.6 and reapply this labeling function. We see the false positive rate decreased to a very small number. After a few iterations of writing and debugging labeling functions, we have many high-quality labeling functions. We now estimate the overall precision. We can click on NaN. The system notifies us to provide labels in the data viewer for a sample of found matches. In the data viewer, we can easily provide labels by left-click to label a match and right-click to label a non-match. We submit the labels, and the estimated precision is updated. As for recall, the number of found matches is a proxy. In addition, we can write as many labeling functions as possible to the extent that we can now find more matches by clicking on the Show button, and this guarantees the overall recall to be high. Finally, we can export the result, including labeled data which can be used to train other-end machine learning models, and the labeling functions that can be used to label a bigger dataset of the same schema.